Welcome you to the Astani Department of Civil Engineering Seminar. Our speaker today is Dr. and Professor Alan Robinson. He's from Carnegie Mellon University. And he is, let's get the right here, among other things, a professor in the Department of Mechanical Engineering. He's also professor in engineering and public policy. And he's a director of the Center for Atmospheric Particle Studies. So I don't know how he had time to do all that, but he does. And he's going to be talking to us. This is his technical lecture, it's our seminar, and he's going to be talking about the work he has been doing on the relationship, particularly the combustion and emissions of organic particles from combustion sources, and how they get out and how they affect the environment and climate. So, and this is one of his primary research areas, so I'm very interested to hear what he's going to have to say. And without further ado, we'll hand you the microphone. There we go. And if you please, you can, there are 8 more people up there, they can sit down.
All right. So thanks for the kind introduction. The mic's working there? Yeah. Did you go? All right. So again, I'm Alan Robinson. Thanks for coming by and listening to my seminar today. And I'm going to be talking about some of my research that I do in atmospheric particles. Of course, there's a a very strong group here in the department that works on atmospheric particles as well. And I think some of the things that I do actually complement pretty nicely some of the activities that are going on. So I'm going to give you a little bit of overview of what I've got going on. And I just want to acknowledge, so this is our center, and I showed a picture of it yesterday. And this is more the graduate student component of the center. And we get funded by a whole bunch of different sort of 3-letter acronyms, essentially. And I've got some of my PhD students listed up there, as well as some postdocs of people who have contributed to this work, and in terms of what we figured out about how these emissions behave in the atmosphere. And I just want to acknowledge the contribution of all those PhD students and postdocs. And I want to point out Albert Presto, who's my research manager, and Neil Donahue, who is a faculty member again at Carnegie Mellon that I work very closely with. So I just wanted to do those acknowledgments before we fire into it. So obviously in this department, certainly a subset of the department is very familiar with what I study, which is atmospheric or fine particulate matter. And so what I'm going to do at the start here is do some definitional talk about what it is and why it's an interesting problem to study and what some of the questions are. So that'll be sort of the first 10 minutes. And then we'll transition into what I've been really working on in terms of thinking about fine particle pollution. And again, it's to give you a sense of the sort of research that I do and the sort of some of the tools that we use and the questions that we're trying to ask. So what is fine particulate matter? Everybody's familiar with it. You're standing on the at the bus stop, and the diesel bus pulls out, and whoosh, my gosh, you're sitting in this big cloud of smoke. Not so much anymore. They've got the fuel control better in the vehicles, but that still occurs. And I guess in Los Angeles now, it's a lot of natural gas-powered buses, but everybody's familiar with that. But in this air that we're here, there's a lot of suspended particles, and if you collect them on a substrate on a filter and image them, a diesel soot would look like this carbon chain that's shown there, and there's some interesting biological particles, and there's a spherical aluminum silicate particle from coal combustion. So just these few pictures of these types of particles sort of illustrates the complexity of the system. And they span a wide range of sizes. You can see there are different shapes. There's complex composition. The diesel soot is carbonaceous material. Obviously, coal combustion particles, aluminum silicate. Multi-phase in the sense it can be both liquid and solid phases, and there are many sources. So it's a very complicated pollutant. Unlike other pollutants like ozone, which is this defined molecule and has these very defined chemical properties and things like that. So health impact. So one of the big motivations for studying air pollution, again, probably doesn't need to be said in an environmental engineering department, but just to get everybody on board is health effects. And here are some, sort of some of the classic instances that motivated, the regulations that were developed in this country. And one occurred very close to where I live. I live in Pittsburgh, Pennsylvania, but Donora, Pennsylvania is a little town up on one of the rivers. There was, I think, a zinc smelter there. And there was an inversion, and pollutant concentrations got very high, and a whole bunch of people died in this small town. In terms of like an acute response to high air pollution levels. And the London fog is another very famous example. Again, a lot of coal combustion for home heating essentially going on, and there was an inversion. It's a combination of emissions and meteorology, and pollutant levels went way up. You can see there's a measure called smoke, which is a measure of pollution, and SO2, which is an air pollutant. And you can see that the death rate went way, way up in the city. You don't need some statistical model, fancy model, to tell you that there's some association here between air pollution and human health. And even after many days after the event, the meteorology conditions had changed, there still was this lingering tail of deaths, and they attribute a very large number of people dying associated with this episode. We're fortunate in the United States that we don't have these sorts of events that are occurring, but certainly in some parts of the world, if you've traveled in China and other places, the pollution is much more severe, and these are certainly still of concern. But because of this, so we've learned more, and clearly the severe pollutant levels are a big issue, and fortunately with our policies that we've improved air quality, but even the lower concentrations that still exist today, there's still concerns. And so here's a plot from a very famous paper from the Six Cities study that was done by the group at Harvard, looking at the association of mortality and fine particle pollution. That's what the plot is showing. Fine particle concentrations on the x-axis, and adjusted mortality, so they were adjusting for smoking and age and a bunch of different factors like that. And there's a strong correlation between fine particle pollution levels. And what fine means is the smallest fraction of the particles that are in the atmosphere, smaller than 2.5 micrometers. And the idea is those are the particles that can penetrate deeply into the lungs, whereas larger particles, we have natural defense mechanisms to help prevent them from coming in. So anyway, so there's still concerns. There's concerns at very high concentrations, but even at the lower concentrations that we're exposed to in the United States. So if you take data like that, estimate, develop a risk estimate and look at a model, sort of look at what fine particle concentrations look like across the United States, you can come up with a map that looks something like this. This was something that was published in Science a number of years ago. And looking at the deaths per 100,000 adults, and you can see the blue colors are obviously lower risks, and then the red are the higher risk where the pollutant concentrations or particle concentrations are higher. And of course, LA, no big surprise, is high, and Pittsburgh up over there is high as well. And it's the urban areas and things like that that we need to worry about. And so clearly this is an issue. EPA has regulations, and tens of millions of Americans live in places where the air is above the threshold, including Los Angeles and Pittsburgh. And so a lot of our work is motivated by trying to develop the fundamental understanding that's needed to develop effective control strategies. So we need to change the emissions in order to bring particle concentrations down to reduce the public health risk, but there's a very complex relation between those emissions and what people are actually exposed to, and studying those relationships is what we work on. So the other big motivating problem for particle pollution is the Earth's energy balance. And so, of course, this is obviously a topic of importance because people are worried about global change. And this is a figure that I took from the most recent IPCC report. It shows the Earth's energy balance. And so the greenhouse, the window, the atmospheric window here, where some of the infrared radiation escapes, is getting closed a little bit with CO2, and clearly this window is units of 40, and so we're closing that. But then you look at the other terms in the equation. It isn't just CO2 and greenhouse gases. Aerosols here, help control the planet albedo, the reflectiveness of the planet, essentially by how cloudy it is one of the ways that it affects that. Aerosols also scatter light back into space, and so you can see that this reflectance term, which aerosols play a critical role in, is a very large number. It's 77. It's bigger than 40, and again, so it's a large fraction that's getting reflected into space. This is the sort of pre-industrial energy balance, and we've put a lot more aerosols into the atmosphere. So what's been the influence here in this circle, and how does that affect the effect of CO2? And if we really want to understand the effect of anthropogenic emissions on climate, we got to understand both. And there's a lot of uncertainty, as we see, about the effect of aerosols. So again, this is a figure from the IPCC report. So this is looking at radiative forcing. So this is looking at the perturbation of the energy balance in units of watts per square meter. So this is sort of the common measure relative to pre-industrial. So long-lived greenhouse gases, you hear a lot about CO2. That's up there at the top. The net forcing at this time they estimated to be about 1.6 watts per per square meter. And there's a little error bar there saying we have a pretty good idea. CO2 is well mixed throughout the whole atmosphere. We can do the radiative transfer calculation pretty accurately, so we understand that term pretty well. And then you can go down and look through the other gases, and they get less important and more uncertain as we move down. But then you look at the effect of aerosols, and there's two shown here. One's called the direct effect. This is the scattering of light, and you can see, well, it's a pretty big bar. It's going the opposite way of CO2, and it's got a big uncertainty bar, right? And then there's an even bigger bar, which is called the cloud albedo effect. So each cloud droplet, right? Clouds are made up of a bunch of droplets, and each of those cloud droplets forms on a particle. And so the question is, have we changed the cloudiness of the planet essentially by emitting a lot of aerosols? And what this is saying is that we have. It's a little more cloudy, and we're reflecting more light back into space. But the error bar is very large, and there's a lot of uncertainty there. In the previous IPCC, the third assessment, they didn't even have an estimate. They just showed a range. And so clearly, trying to constrain this better and understanding, what that role is really important, and that's another sort of motivation for the research that we do. And we actually work on this problem as well. So the other thing that's come up, in terms of thinking about things as climate, there's someone named Paul Crutzen. And so Paul Crutzen is a very famous person in the environmental science field because he won the Nobel Prize for the ozone hole. And a number of years ago, he wrote this editorial in the journal Climatic Change, which sort of created a lot of furor. And what they were talking about is essentially what's called geoengineering. And so geoengineering is going and intentionally manipulating the climate to try to counterbalance some of these things that are going on. And one of the strategies is to basically put sulfur into the stratosphere, make a lot of sulfuric acid particles in the stratosphere, increase that scattering term a little bit to offset the sort of closing of the window associated with the greenhouse gas emissions. And he was saying, well, we haven't shown much progress in managing the CO2 side, so we got to put this on the table. And there was sort of a furor that sort of came out when this occurred about, the popular press sort of picked it up, and it's something that scientists haven't talked a lot about, but there's more work that's going on, and there's certainly some discussion of a national research program in this area to try to address these sort of key uncertainties. It's a pretty scary idea, geoengineering, but certainly atmospheric particles and their behavior is critical. So now getting a little more into what I do, and certainly this relates to what goes on at USC in this area, is in the end what we're worried about are these effects, whether it's an effect on climate or human health. And then what we manipulate are the emissions, right? So we need to understand what the relationship is between those emissions and health effects. And so what my research focuses on is sort of the beginning of this chain. I work sort of in the emissions at the end of the tailpipe and try to understand how those emissions are transformed into the atmosphere, and think a little bit about exposure, but certainly not closing the loop between that exposure and health effects is something that there's, I think, a big need that some of the stuff that I do could contribute a lot to, but it's not an area that I've worked on. It's something we've tried to get into, and we haven't been successful so far. So these are atmospheric processes, mixing in the chemistry and the microphysics and things like that are going on that are determining essentially the exposure levels of the pollutants. And we take a pretty comprehensive approach. So there's a number of us at Carnegie Mellon, a pretty big group, and we do emissions characterization. Here's an example of a student of mine. We're doing some stack testing. Field studies, we've run a number of field studies. We do field studies all over the world in terms of measuring particle pollution. This was a very large one that we actually ran in the Pittsburgh area with investigators from 20 different research groups that came to Pittsburgh to bring sort of their world-class techniques. Actually, Costas came as part of that. We do a lot of laboratory work as well. So we look at what's going on in the field, and then we do a lot of laboratory work. We have a large lab. Do chamber studies to try to do more controlled experiments to try to mimic what's going on in the atmosphere. And then finally we do modeling, both receptor modeling, which Ron is an expert, an international expert in, and then emissions-based modeling. And these are the sorts of tools that EPA will use often to sort of set strategies. If we're going to reduce sulfur emissions from coal-fired power plants, how much do we need to reduce them to get, Topeka, Kansas into the standard, right? So you got to connect those emissions, and the way they do that is with these emission-based chemical transport models. And a lot of our research in the field and emissions characterization is designed in lab experiments. We're designed to get data to use in these models, and a lot of the field studies are often used to evaluate these models because they sort of represent kind of our conceptual understanding of what's going on. So now getting into mine, I work on the sources. As I already said, there's a complex array of sources. Cars and trucks, boats, cooking. The natural environment is a big source. All these emit both gaseous and particle pollutants, and we need to understand the relative contribution of all these sources if we're going to develop effective control strategies. So if we're going to think about the contribution of a combustion system to ambient fine particulate matter, you need, okay, the stuff's coming out the stack. And so you can see it. Whoa. Okay, that's the right spot. I was thinking things got messed up. So there's one category that we call primary PM, and that's what you can see in the picture, which are the direct emissions of particles, stuff in the particle phase, soot and things like that. So obviously we're going to need to understand that contribution to ambient fine particulate matter. And you can divide that primary PM into a couple of categories. One is what would be considered non-volatile PM, which is essentially PM that material that exists in the particle phase at the point of emission, at the high temperature, high concentration conditions at the point of emission. So it's refractory material, soot, trace elements, fly ash, things like that. And then the other component is volatile PM, primary PM, which is the organic component and the sulfate component. And this is material that actually exists as vapors at the point of emission, and it's transformed in the atmosphere physically, a partitioning effect into the condensed phase to create some primary PM. So we're interested in that volatile component as well. So this is one chain, and we need to understand the contribution of the emissions from the diesel, both of these boxes, and we will see how hard or easy it is to understand what that contribution is. The other one that's very important, actually from a fine particulate perspective, maybe more important, certainly the data indicates, the ambient data, is secondary PM. So this is PM that's formed in the atmosphere from chemistry. So gas phase species go into the atmosphere, they react in the atmosphere, and some of the products of those reactions actually then form particulate matter. And so it depends on this nonlinear atmospheric chemistry. So that's a critical component. If you look at the ambient data, the majority of fine particulate matter comes from this pathway, most of the time. And then you can sort of further subdivide it and think about there's the inorganic constituent, things like sulfates, which are from the oxidation of SO2 emissions, mainly from coal-fired power plants. And then there's this organic component called secondary organic aerosol, which forms from reaction of volatile organic compounds in the atmosphere to form low volatility products, which then condense into the gas phase. So it's important to realize that all these boxes on the right here, these three, all exist at vapors at the end of tailpipe. And so these atmospheric transformations of this material is going to determine the ultimate impact of those emissions on ambient concentrations. And so my research focuses on those boxes and thinking about how to model those and represent them in models so that we accurately predict what's going on. And I'll talk about some of our advances in our understanding based on looking at that. What's really regulated right now is primary PM, right? There's a diesel test standard, 10 milligrams per mile for a tier 2 vehicle or whatever that, ARB, there's certification testing that you do, and very elaborate procedures to determine that, but that's regulated. We can then think about how well what they measure is actually related to what's in the atmosphere. That's another question. And then the other component that's very strongly regulated is the inorganic component. So like SO2 emissions from coal-fired power plants are heavily regulated, NOx emissions are heavily regulated. But the organic component isn't as heavily regulated. There's VOC regulations for ozone, but not really targeted at the secondary organic aerosol component. So now we're going to shift gears and get into what, specifically. So I work on those boxes that are the stuff that's vapors as it leaves the combustion system, and then I work on a subcomponent of the aerosol. Remember I said it was a multi-component, lots of different materials, and what I really work on is the organic component, which is this really complicated mixture of molecules that we don't, if you try to go and identify that material on a molecular basis, you can only identify about 10% of the mass typically on a molecular basis. Most of it we can't identify with sort of existing analytical techniques. And it's a big chunk, and it's a big chunk as you'll see across the country. And all these bars here is the sort of volatile primary and secondary, the stuff that exists as vapors, and it's more than 80% of the mass. And so these atmospheric transformations are essential for understanding. So I'm going to work on the organic component. That's my focus, as Ron said in the introduction. Here's data from all over the world from an instrument called the AMS that they've made these measurements, and I'm not going to go into the details except that the pie charts indicate the chemical composition of the aerosol, and the green wedge of the pie chart is the organic component. And what you can see by looking at this graph is certainly the relative size of the different components is varying, but the organic component is very significant in all these places. And so understanding the sources of that material, it's not well understood, and it's a significant component. So it's actually an area of very active research in the air quality and atmospheric chemistry community. So that's sort of a motivation for organic aerosol. And so the prevailing conceptual model for organic aerosol was this until some of our work, and we're still, certainly the community is wrestling with some of these ideas, but I'll throw out my version of it. And so primary organic aerosol, essentially how it's treated, and this is in the context of chemical transport modeling, right? And so thinking about an emission inventory that goes into these models, the primary organic aerosol is measured as non-volatile and is simulated or treated in the model as non-volatile and non-reactive. So essentially it's these little pebbles, well not very, very small pebbles that are floating around in the model, and then they deposit and they disperse, but they're relatively uninteresting in terms of their dynamics. And that's the way most chemical transport models treat that, in certainly all before the work that we were working on. And then secondary organic aerosol formation in these models is really treated with basically a small number of what I call high flux but very volatile precursors. So things like single ring aromatics, toluene, benzene, compounds like that are thought to be very important from anthropogenic sources, then monoterpenes, which are emitted by biogenic sources. And then there's an absorptive partitioning model that's used to simulate that, and we'll talk about that. But that sort of was the prevailing conceptual model, this sort of very non-volatile, non-reactive POA, and then a very small number of sort of secondary organic aerosol precursors. And work at Caltech by John Seinfeld certainly has been instrumental and certainly in the secondary organic aerosols. And if you implement that in one of these chemical transport models, this is some work that one of my students did, but I mean the point of this graph isn't the numbers, but just the sort of general thing that the model is predicting is what I've got plotted here is just a intensity plot in the ratio of primary to total organic aerosol. So the fraction of the aerosol that's primary in blue says that it's mostly primary, and red says it's mostly secondary. And you can see over these urban areas where the non-compliances and things like that, it's very blue, which indicates that in the summertime, even in the summer, it's mostly thought to be these, with the sort of prevailing previous conceptual model, thought to be mostly primary. So if we're thinking about developing control strategies, well, if it's mostly primary, well, we got to go after those particles at the point of emission, right? As opposed to thinking about getting precursor gases, which are forming the secondary aerosol. So that's what the models were predicting. And it looks something like that. But then we look at field data, and there's lots of different pieces of field data. And this is just one, again, from this same study. And this, again, was using an aerosol mass spectrometer, which is an instrument that gives you some information about the chemical composition of the aerosol, and you can actually separate it into factors to get some estimates of what the relative importance of primary and secondary. And the pink areas are the secondary. And so this is, again, that data from that map that I had before. And what it's showing is that even in urban areas, it's mostly secondary organic aerosol. And so this is surprising, right? That's where the sources are there. And you would think that if any place, that's where the primary is going to be highest. Whereas the model was predicting like 80% primary, where here they're seeing only about a third is primary. And then as we move downwind, which is another feature that's not captured in the model, there's this transformation where we go from the sort of primary wedge, which is the gray wedge, gets smaller and smaller and smaller. And in rural areas, it's completely dominated by secondary. And the models weren't predicting this kind of transformation that was going on. And so there's this disconnect between what the models were predicting and what's sort of observed in the ambient. And we wanted to try to address that and try to understand what was going on. And it's important for a couple of reasons. One is that if you want to develop a control strategy, you've got to know which component of the emissions you need to go after. And then if you want to think about health effects and stuff, that the secondary organic aerosol presumably is going to have a different toxicity and things like that. There's certainly data that indicates than the primary. And so there are a lot of people doing health studies, rat inhalation studies with diesel exhaust, and but if everybody's being exposed to more secondary aerosol, how do you interpret that? And then obviously, so we looked at these two things. There's this disconnect, and so here's some modeling. This was done by Alma Hodzek at NCAR. I guess it's actually an ACP now, and so it's looking at a sort of observed based on this AMS estimate over model predicted for secondary organic aerosol. And you can see this. She compiled data from a number of different studies. That's what the acronyms show. And then she divided it into sort of urban areas and outflow regions and remote, kind of the same way. And you can see that there's across the board this consistent sort of very large systematic underestimate of the amount of SOA. And so we'll come back to this graph because Alma actually has implemented our ideas into this model named Shamir and run it and tried to see if she could improve the model performance. And we'll come back to this graph and you'll see that it improved it a lot. And so we saw these issues. And we were interested in sort of stepping back, right? We have this conceptual model. Can we test that model and think about, are we missing, is there something missing in our framework? And so we stepped back and said, well, let's think about the processes that occur after the exhaust leaves, the tailpipe. There's this initial dilution of the exhaust that happens very rapidly. Within a second or two, it's diluted 1,000 to 1. And then that dilution continues out for minutes until it gets pretty well mixed into the regional background. And so we need to make sure that we understand what's going on there, and we've accurately represented that. And then in the atmosphere, the stuff floats around for a week or more, where it's oxidized and things like that. So trying to understand this transformation that occurs, near the source all the way out to regional and continental scales. So how can we go about studying that? And so I'm an experimentalist, or I do a bunch of different stuff, but I'm an experimentalist partly. And so we want to study this in the laboratory. And how can we do that? Well, we can use a device called a dilution sampler, which mixes exhaust with essentially ambient air, conditioned air, to simulate those processes that occur really close to the engine exit, or to the end of the tailpipe, that rapid mixing that initially occurs. So this is an experimental system that you can kind of simulate different mixing rates and this sort of stuff to try to understand what happens sort of in the near field. And then you can investigate longer time scales with what we call as a smog chamber, which is essentially a special room about half the size of this room that's got a big Teflon reactor in there. You can put the emissions in there and then study how the chemistry of those emissions evolve over time. And we've done this for a bunch of different sources: aircraft, engines. Actually, we've just finished a very large light-duty vehicle test campaign up in El Monte with the Aerosols. We're going to be downtown LA at the MTA facility in a couple months doing this. Wood smoke, open burning. So getting data for a bunch of different sources to try to test some of these ideas. So what do we learn? And well, first we can think about kind of this near field effect and thinking about what is primary organic aerosol, right? This is the sort of directly stuff, organic material that sort of ends up in the condensed phase in the atmosphere without undergoing chemical reactions. So there's a physical change in partitioning that people were aware of, but we want to understand that those changes a little bit better. So thinking about some of the work that was done by Glenn Cass at Caltech, I mean, so if you make the measurements, and other people in the engines community have done, you've made the measurements, at the high temperatures in the exhaust, the primary organic aerosol emission factor, so it's grams of primary organic aerosol per kilogram fuel, and I've got it plotted as a function of dilution ratio, which is kind of, as the exhaust mixes as it moves out. If you measured at the hot temperatures in the exhaust pipe, you don't measure much, right? There's not much stuff in the particle phase, and essentially the temperature is too high, the stuff exists in the vapor phase, not in the particle phase, right? Clausius-Clapeyron exponential relationship between vapor pressure and temperature. So if you throw a dilution sampler onto it and then say, well, let's cool it down to ambient temperatures, and it doesn't take much dilution to cool it down to ambient temperatures, 10 to 1, 15 to 1, you get it down to ambient temperatures, boom, there's a lot more organic aerosol. Essentially, we've undergone this phase transition from the high temperature where everything was vapors to much colder temperature where things are in the condensed phase. And so they have a very nice paper in the journal Aerosol Science and Technology from about 20 years ago where they sort of demonstrate this phenomenon, and conceptually it makes a lot of sense. But the reality is we're not breathing 50 to 1 or 20 to 1 diluted air, right? I mean, it's a lot more dilute than that. And so, and most of that dilution actually occurs isothermally, right? There's this adiabatic mixing, it gets to ambient temperature relatively quickly, it's an easy calculation to do, but the concentrations are often much higher than ambient concentrations, and partitioning also depends on concentration as well. And so what had been done before what we did, I guess I'm a little out of order, is that at this point they said, well, we've captured the sort of dilution phenomena, been sort of suggesting that we haven't, and that's what we'll see in a second. And then what we've done is we've taken those measurements and used those as our emission factors in our chemical transport model. And say, okay, we got the right answer, we captured this near field effect, we can just apply that, whatever we measured in our dilution sampler, sort of across the full range of atmospheric conditions. And what we said is, well, my gosh, that's not as dilute as we want. You look at theory, it suggests that things should start to evaporate. And that's what we did. So we did experiments at much higher dilution ratios that's typically done. And what we saw is that the aerosol started to, the mass started to decrease, mass per unit fuel. So we've essentially, by plotting things as a fuel-based emission factor, we're accounting for the effects of dilution in terms of, an CO or some inert species will just be a straight line like that non-volatile. What you can see is the mass emission factor is going down, and essentially what's going on is the organic aerosols evaporate. So the concentration is going down. This is what theory, the second law of thermodynamics, essentially would suggest should happen if you've got a semi-volatile aerosol. So we saw this, and so we're like, oh, it's not clear that those primary organic aerosol emission factors that we measured at low dilution ratios in our dilution sampler, essentially at number 2 there, are going to be representative of what's out in the atmosphere. So again, I already mentioned sort of partitioning theory. So this is essentially the second law of thermodynamics, which you then can recast as Raoult's law for an ideal solution. And then for the atmospheric sciences community, the way we plot it is, or write it, is something like this. And we've got everything expressed in terms of the sorts of variables that we measure in the atmosphere. And so XP is the particle fraction, so the fraction of that material that's in the particle phase. So if it's a semi-volatile material, it's partitioned in both phases. And that's a function of the effective saturation concentration or saturation vapor pressure of that species, right? And we call it C star, and we think about it as an effective saturation concentration, which is just analogous to vapor pressure, because in the atmosphere we're measuring mass concentration. So it's a very easy, you know, if you tell me what the C star is, I know what typical atmospheric concentrations, I already immediately know something about the partitioning. And that's going to depend on both the temperature of the system, and then there's some mixture effects which we can account for with an activity coefficient, which are very poorly understood. And at this point, models generally assume that it's a pseudo-ideal solution. And then again, it's a sorptive process, right, like Raoult's law, so it's partitioning into this organic solution, and so we need the amount of organic aerosol in the system is going to be important as well. So we've got a term here, the temperature term is in here, the numerator, and then in the denominator we've got this sorptive material. So we've got this competition that's going on. And essentially what's going on is, as we isothermally dilute, you know, what theory says, and this is just sort of a cartoon illustrating, is that essentially there's going to be gas to particle conversion, evaporation of the particles to maintain phase equilibrium. You need to keep the Gibbs free energy of those species in each phase to be the same. So how can we sort of represent this in models? And the challenge, of course, as I said, is that, you know, we only know about 10% of the mass on a species basis, right? And so we don't know most of the mass. And so if we knew all the species and we knew their thermodynamic properties, we could put this in a model and predict the phase partitioning behavior, but we don't know what the composition is. So we need to take a more of a semi-empirical approach, and that's what's illustrated here. So essentially what I've got is particle fraction. This is the XP parameter, so the fraction of the emissions that are in particle phase, or a fraction of the emissions, a certain component of the emissions that are in the particle phase, as a function of concentration. All this data are at 25 degrees C. You can see there's this very sort of systematic trend in the data, which suggests that at high concentrations, a milligram per meter cubed, a very large fraction of these organics are in the particle phase, and as we dilute to more atmospherically relevant concentrations down here, a very small fractions in the particle phase. And all the data from many, many, many experiments, you know, there's certainly some scatter, there's experiment to experiment variability, there's some uncertainty, but there's a very clear trend here, and we can essentially fit this equation in a semi-empirical fashion to determine what we call a set of surrogate compounds that we can use to describe the partitioning behavior. And that's what we call the volatility distribution. And you can represent that down here, say, with this equation. What we want to find is essentially the mass fraction of the emissions that are in each of these kind of C star bins. And so essentially we can represent the partitioning behavior of these emissions by fitting essentially this solid line of best fit, which corresponds to that volatility distribution. So we can represent that behavior, this partitioning behavior, with this set of surrogate compounds, essentially. And then we can then put that into the model and predict for a range of different atmospheric conditions how that partitioning behavior is going to change and how the amount of organic aerosol is going to change. So we're applying theory to the data, and so we do some nonlinear fitting to derive this. And there are other ways to go about measuring this. I'll just show you one, but there's, you know, there's temperature ways, that's the other lever you can work on. We're working on some chromatographic-based ways of measuring this and things like that. But this is some of the things that we were doing. And so one of the implications is that the amount of PM emissions are not constant. So this is from a review paper that just got published that we had written in terms of thinking about this and thinking about this PM emission factor. Now what we're trying to do is represent it over a range of atmospheric conditions. So it's the same kind of partitioning plot. There's sort of this non-volatile component that I talked at the beginning, which is constant. It's not going to depend with changes in aerosol, the atmospheric concentration. This again is grams per kilogram fuel. But then the sort of volatile component, we've got this very dynamic change in partitioning. And so you can't represent it with one number, which is how we've been representing it in the model before. The reality is it's spanning all over this blue area, which is the sort of atmospheric range from, you know, a microgram per meter cubed up to, you know, 50 micrograms per meter cubed. So if you represent it with one number, hopefully that number is at least in the range, right? So, you know, then you're gonna, these are going to be your errors. But often what happens when we do source testing is often the concentrations are much higher than atmospheric-like concentration, so your data point isn't even in the range that you want to try to represent in the model. And then finally, the CFR specifications, so how they do source testing for diesel engines, requires it to be at 47 degrees C, which again suggests that there's going to be a bias flow. And the idea there is, 47 degrees C is very comfortable. You don't have to worry about condensation of water and things like that, but the atmosphere is not 47 degrees C. And so the partitioning measured in these systems isn't necessarily representative of what's going in the atmosphere. So the traditional approach for measuring these emissions and constructing these inventories was this, right? So this is the behavior that we've observed. This is what theory would suggest, and this is what we've observed experimentally, is they would measure the emissions at one point at some low dilution ratio and construct an emission inventory represented in volatility space here with C star versus emissions. This is the national emissions inventory for the United States used in chemical transport models. You can see that essentially there's this very big non-volatile PM component which is very dependent on the conditions at which you measured the emissions, and then this is the VOCs that participate in ozone chemistry and secondary organic aerosol formation. So the new framework that we've proposed is actually, it's more complicated, but it's more physically based, and it tries to capture this dynamic behavior, which we argue is really important because the atmosphere is out here, whereas the source testing is done here, so we need to represent those changes. So what we need to do is we need to take these sort of emissions, which are assumed to be non-volatile, assigned to a C star of 1, and distribute them across this volatility distribution by measuring the partitioning behavior. So it's this new way to represent these emissions and understand their dynamics in the atmosphere and better predict them in models. So that's part of sort of this new conceptual model that we've developed, is that component. And as I've already sort of illustrated or suggested, is that there's a lot of evidence that these traditional primary organic aerosol emission factors using these models are pretty biased. So what this is plotted is this emission factor bias. So this is kind of the emission factor. This is calculated based on some of our partitioning curves. This is the implications of what our results say. And certainly for our sources we've demonstrated this, but we're saying more generally it's true. So if you look at our emission factor that's measured at a dilution sampler at some condition, 100 dilution ratio of 100 or something like that, relative to what the concentration should be really at the emission factor at atmospherically relevant conditions across a range of dilution sampler measured organic aerosol emission factors. I guess the plot's a little bit complicated, and the ratio of 1 means that there's no bias, and what you can see is that for most of these sources that we've got listed up here, there's going to be a very large positive bias in this emissions data because they haven't conducted the experiments in a way to sort of accurately represent what the gas particle partitioning is in atmospheric conditions. And the only way you can get around this, there isn't one answer, is actually by dynamically simulating the partitioning. So one of the implications is that a lot of this stuff that we were assuming was sort of non-volatile particle stuff floating around the atmosphere actually is vapors in the atmosphere, right? The stuff evaporates, it actually exists as vapors. And that's what's shown here. It's the predicted partitioning of diesel exhaust at some typical atmospheric condition. The red is the fraction of the emissions that are in the particle phase, but you can see there's a lot of blue, which is stuff that is in the vapor phase. It isn't accounted for in models right now. And so what we were interested in is, well, what happens to those vapors when we age it, right? So we've got this dynamic partitioning that's going on. It's a physical process, due to temperature and changes in concentration. And certainly what we observe is very consistent with what you would expect based on theory. And so what happens if you age? And so these aging experiments we've done is we take some exhaust, so this is looking at these longer time scales, put it in a little bit of exhaust into these smog chambers and sort of study the atmospheric evolution of that material. And we do that using a variety of instrumentation that measure both the gas and the particle phase to try to understand, again, how the chemistry is going to influence the phase partition. And we do that, again, we put the exhaust in, we got a bunch of instruments, and then we either expose the exhaust to just natural sunlight, or we have, basically simulated sunlight as well. So what do we see? Well, this is from aircraft exhaust, measured at 4% load. So that's a sort of a ground idle sort of operating condition. So when you're number 56 at LaGuardia, this is what's going on. And essentially what we see, the experiment, this is showing the primary aerosol emissions are shown here in gray, and at time 0, we expose the aerosol in the chamber. So we've sampled this behind an aircraft. I'll show you a picture of how we do that in a bit. And what we see is, wow, we generate an enormous amount of secondary organic aerosol, a little bit of secondary sulfate. And if you look at the ratio of this with the primary PM, you can see that after an hour or two of sort of exposure to the atmosphere, the actual contribution of this aircraft is 20 times higher than what you would have predicted just based on the direct emissions, right? So secondary aerosol dominates. A ratio of 20 is very dramatic, and I like to show the aircraft example because this is the one that's by far the most dramatic. We've done this for a variety of different sources, and the ratio is more typically, a factor of 2 to 5, but a factor of 2 to 5 is still a pretty big deal as well. And here's for some diesel experiments. That was the original one for wood smoke. Here's some open burning data. There's the aircraft data. And again, the format's always the same. It's the non-volatile primary, and then it's looking at the secondary organic aerosol. So it's suggesting that there's a lot of dramatic production of secondary organic aerosol, from the exhaust of these combustion sources. And the amount of production we see is very consistent with some of this field data, where we already talked about the models weren't able to reproduce the field data, but this is a parameterization from Joost de Gouw, who's at NOAA in Boulder, and they fly aircraft downwind of the eastern United States and look at the production rates, and they can look at the photochemical age of these air masses and parameterize the secondary organic aerosol rate. And what we're observing in the chamber is very similar to what has been observed sort of downwind of these urban areas. So that, it seems like we're doing an okay job of that. The other thing is, well, what if we take one of these models and actually sort of create a box model, say, and try to simulate what's going on inside of our chamber? We can take essentially the chemistry model that's being used in these big air quality models and just run it for our chamber. And we've got a lot of measured data, so it's easy to run the model. We're measuring the decay of the VOCs and things like that. So we can try to say, well, how much would the model predict given the oxidation that we've actually observed in the chamber? We're not even predicting the amount of oxidation, we're observing it. How well would the model do in predicting what we observe? And we don't predict very much. And this is exactly what the models are predicting in the atmosphere, right? So there's this disconnect again. So this is the same thing that's been observed in the atmosphere, we're observing in the chamber. In this phase, we've stepped back and said, well, let's look at the whole emissions. Let's not assume that it's just a few species. Let's think about the whole emissions. And then we got to go try to explain some of the unexplained SOA. And that's something we're still working on. And this was, a paper that we had in Science a couple of years ago. So what is the source of that unexpected XOA? I mean, I don't know if it was unexpected. We've sort of observed it in field studies and things like that, but we need to start explaining it. How do we, account for it in our models and our source testing and things like that? So one, hypothesis would be, well, the data that we have for these traditional precursors isn't right? The yield data, essentially, when you oxidize toluene, how much secondary organic aerosol you get, well, maybe they're off by a factor of 10, right, or something like that. There's been a lot of data. People have really tightened the screws. I think Leah Hildebrand was here. I don't know if she talked about some of her toluene experiments that she's done in our laboratory. But essentially, you'd have to increase the yields by like 10 times. And you run into mass balance problems and all this stuff. It's hard to explain it that way. I don't think, maybe that's contributing a little bit, but I don't think that's the explanation. So our argument is that we're missing precursors, essentially these low volatility gas phase vapor species that we talked about earlier that are not in the models, essentially. They're not represented correctly in the models. And if you look at it, do a simple kind of back of the envelope kind of mass balance calculation, there's plenty of this material out there that generate a fair bit of secondary organic aerosol. And so at least from a mass balance perspective, it would work. The problem is we don't know the molecular identity of these species. And so if we want to develop a mechanism, it gets challenging. So what's going to happen to that material in the atmosphere, right? So if we're thinking about the chemistry of this in the atmosphere, we don't know what it is, but we do know, the basics of what the chemistry would look like. And so if you think about these as saturated hydrocarbons, and they're getting attacked by the hydroxyl radicals, the primary oxidant in the atmosphere for these species, you get blue. This is sort of a map of what the chemistry might look like. And essentially, the bottom line is, if you think about the sort of first generation of chemistry, there's a key branching here, depending if you've got a lot of NO, so urban-like conditions would go down this branch, more rural conditions would go like down this branch. Then I've got a bunch of colored sort of circles here, which are kind of the first generation products. So we get the initial oxidation by OH, and then this kind of stuff happens pretty quick. We end up with a bunch of species here, nitrates, carbonyls, acids, and each of those species, we can look at what the change in volatility of that, and that's what's shown on this diagram. So the yellow is the parent compound, and most of these products, the volatility is lower, right? This is how we generate secondary organic aerosol. We're taking a very volatile precursor. The products have some oxygen on them. They have an acid group, which reduces the volatility by about a factor of 1,000. You take a hydrocarbon, throw an acid group on it, it's much less volatile. So you get this distribution, and most of the material has lower volatility. You can see everything is shifting to the left in the volatility distribution, closer to the particle phase. There is pathways where you basically break the carbon backbone. You get these two little smaller fragments that'll make stuff more volatile. But at least initially, that sort of fragmentation pathway is not thought to be very important. Essentially, you need to get a lot of oxygens on the carbon backbone to, to start making it basically more unstable. Anyway, so this has been figured out by looking at a bunch of individual compounds, and we think it's this complicated mixture of hydrocarbons, and this is what the basic chemistry should look like. So we can take that basic chemistry, and there are a number of ways to try to implement it and try to start aging this material. And this again is just the result, and not showing all the details of the chemistry and stuff. But the bottom line is it's saying at the kind of yields you would expect from these sorts of compounds, the rate at which it's oxidizing, the amount of it that's in the system, that the pieces of the puzzle sort of fit together reasonably well. This, of course, is reasonably semi-empirical, but certainly the rates. If you take this and you generate an aging model, so essentially this model has been fit to the data, but you look at what the fitting parameters, the rate constants, and the yields, they're exactly what you would expect for the sorts of compounds that we expect to see, and there's enough mass there. So essentially, that this volatility basis set aging model, so if we take these emissions and age them, we can explain a lot of what we observe. And so a number of groups have implemented this, and it's actually being implemented by EPA and others as well into these more regulatory models. But this is some of the work from Alma Hodzic, again at NCAR, and so she implemented this framework and did a number of different simulations, and you can see the red bars are the results of the model with this new framework, both treating the aerosol, the primary organic aerosol semi-volatile, as well as treating this oxidation of these low volatility vapors. Certainly there's a bunch of uncertainty, right? I mean, there's more work that needs to be done, but certainly there's a lot of excitement in the community that this seems to be an important sort of conceptual step forward in terms of thinking about the system, and now there's a lot of work to go and sort of really implement it rigorously, and that's what we're working on now. So this is sort of the new conceptual model, which is for a much more dynamic system than has been sort of understood in the past, and it's really, thinking about, both the sort of dynamic effects of dilution and chemistry. And so we have this kind of particle to gas conversion that's going on, and then we have this gas to particle conversion as we move from sort of near source scales to regional scales, which are changing both the amount of the aerosol that's there, as well as changing its chemical character, and potentially changing its impacts on climate and changing its impacts on human health. And so if we're going to use these models to try to simulate what the effects of particles are on clouds, I mean, this stuff coming out of the diesel engine doesn't affect clouds very much, but that oxidized stuff in the atmosphere does, and so we need to worry about these transformations. So evaporation, repartitioning, the photochemical agent. We have a much more dynamic system now. So this is, again, a cartoon, thinking near source out to kind of these regional scales. So the old model was concentrations would decrease as we moved out just due to dispersion and deposition. In the new model, they would decrease a bit faster due to this evaporation, essentially. But then as we get to the longer scales, urban and metropolitan scales, the secondary chemistry kicks in, which is a little bit slower, and you have this production of mass. And we, of course, need to understand what the relationship of these two curves are. And so clearly a big question mark is, well, how much decrease do you have, and then how much sort of increase do you have at sort of the urban scale. So I think there's a lot of evidence that this is the process that's going on, but there's a lot of PhDs that need to go in to try to nail down those details. So the revised model, as I already showed, it brings if you put this framework into one of these chemical transport models, it brings the predictions into much better agreement with the observations. So this is just, again, illustrating. I already showed that with the data from ALMA, but this is, just illustrating. This is the map we looked at before, suggesting it's mostly primary, and all of a sudden it's mostly red, right? And this is what we observe in the atmosphere. The transformations that occur in the atmosphere, we had a paper in Science, I guess, last year on that, much more consistent with that. Implications for source testing, simply dilution sampling at one condition is not enough. How can we measure the properties of the emissions that are going to control the atmospheric behavior? And thinking about, we've figured out how to do it, I think, from a scientific research perspective, but from a regulatory perspective, I'm doing a lot of work with CARB. There's a lot of interest there about how can we get this into our models? How can we get it into our surveillance program? How can we modify the way we're doing source testing to do this? And so I think there are a lot of interesting implications for source testing. Implications for inventories. I've already showed you how we've remapped these non-volatile primary into this distribution here. There's some questions of missing emissions. Are the techniques that we're using capturing all the organic emissions? And there are important, interesting research questions there. Control strategies, questions for control strategies. So NOx, SOA formation depends on the VOC to NOx ratio, which ozone chemistry depends a lot on. And so, you know, given that it's mostly secondary, the models aren't predicting it's mostly secondary, but that's what the observations say. You know, what happens when things like CARE or the transport rule, which are going to change essentially the oxidation state of the atmosphere by reducing NOx emissions from coal-fired power plants in a big way. What's that? Are all of a sudden we're going to make a lot more secondary organic aerosol because we're going to do that? So we need to understand those details because there may be some unpleasant surprises that aren't accounted for in the models. Human health, this is a slide from Costas's group. Looking at the health effects, and this is data that's been collected in Los Angeles, and looking at the toxicity associated with this particular test, and plotted as a function of dilution ratio. And the interpretation was when that semi-volatile material was in the condensed phase, it was much more toxic than when it was in the vapor phase. And so again, maybe this semi-volatile material is very related to what's going on with some of the toxicity. And that, of course, is, you know, the multi-billion-dollar question is, you know, what component of the PM is causing these health effects that we see, so we can target our regulations a little bit better. So I think there's a lot of opportunities here to think about these transformations that we've been studying and think about them in the context of human health. So next step, so what are we doing now? And so, well, I mean, we developed this conceptual model, we took some data with a couple of different sources in the laboratory, and one of the key things is, you know, there's certainly a bunch of skepticism. Well, the little diesel engine you used in the lab, you know, there's one of those, and there's in your lab. You know, this is true more generally. And so, well, we've put together the resources to go out and test that. And to do that, essentially, we've developed this mobile laboratory, which is a kind of a, you know, the $29.99 U-Haul, essentially, but, you know, with $1 million worth of instrumentation in it, that we can essentially take our laboratory into the field that we've been doing at Carnegie Mellon. I can't bring a KC-135T to the lab. Right, so here we are at the airport. We've got a transfer line to sample behind the engine. We've done aircraft, we've done helicopters. I'll show some other stuff. There's our portable smog chamber. We've done some other tests. So we were at the Fire Science Laboratory in Missoula, Montana. There's this huge warehouse, really cool facility, this huge warehouse where they burn big piles of, you know, combustibles. You know, wildfire relevant fuels. We were there for about 6 weeks studying the atmospheric evolution of these wildfire emissions. As I said, we were at the Hagen-Schmidt lab in El Monte in May and June of last year and tested about 50 in-use vehicles recruited from the California fleet, trying to understand this for in-use gasoline vehicles. We were at Wright-Patterson Air Force Base doing some helicopter testing. We're going to be at the MTA facility in a couple months doing heavy-duty diesel testing. We're doing some non-road. So there's this big effort now to go and collect data to test the conceptual model with a bunch of different sources, get data from these different sources so we can improve the representation of emissions for the chemical transport model and improve the representation for the aging. And so this is an enormous effort and takes a lot of people to do it, but it's exciting and fun work if you like to be in the field. So this is one of the directions that we're sort of headed right now. And so I think hopefully I'm about on time. But thanks for your attention. I'd be happy to try to ask any questions, but it gives you a sense of what I'm working on. Questions?
I'm not in environmental engineering. You show a lot of results in terms of 2D graphs and histograms. But you're conducting an experiment. How many parameters do you measure at the same time with that particular data point? Like actually you measure temperature, how many parameters typically go with a given measurement? Well,
so it depends how you define parameters. So if you look at, the basic set of data, right, would be some concentration data for a number of different pollutants, right? So you can think of organic aerosol as one. You may measure it with a couple of different techniques. You'd measure some sort of environmental parameters like temperature and relative humidity and things like that. If you're running the mass spectrometer on it, you'll get very complicated mass spectra of what the information on what the chemical composition. So mass to charge ratios of 100 mass to charge ratios of the aerosol. If you're running the high resolution one, you may have thousands of essentially data points. So there's a lot of different data, and one of the things that we do try to do is to try to use multiple techniques that use different principles. They're trying to measure similar things to make sure that what we're seeing isn't sort of an artifact of one of the measurements.
Okay, so if I understand correctly, the answer is it depends on the experiment.
Depends on the experiment.
Could be a lot.
Generally, it's a lot. We try to measure.
Okay, so how do you analyze this? Like you show very simple trends for general public. But how do you try to understand the physics behind it and chemistry behind it? Do you have the regression models that have 120 parameters in them?
Well, I mean, that would be taking a pure statistical approach. And so what we do is we
No, regression models. No. You have a hypothesis and you're testing it.
Okay, so this...
That's basically my question.
Yeah, so that's what this is, okay? So this graph here, so as opposed to just applying a regression model, what we've done is we've fit, this is what theory would suggest, this is the second law of thermodynamics, suggests that this is the behavior that we would observe, right? So that it certainly falls along and then you can fit, so there are a couple of parameters, you need vapor pressures and things like that. So essentially we did, fit a regression model, a nonlinear fitting here, to basically say, well, how well can we describe this data with this model, right? But it's semi-empirical in the sense that to really run the model, you would need to know all the chemical species, right? To run it, say, from first principles. So what we're doing is fitting and saying, well, certainly the behavior is exactly what you would expect from this model, which is physics-based, as opposed to just doing a statistical model, and then you can get this representation. So does that help address what that question is?
Yes, but this, to me, from an analysis point, this is like first order. Now, how about second order, third order?
Well, so
terms that might help you see what's going on.
So what we have is, so we have the physics and the chemistry, right? So we've got the second law of thermodynamics and things like that. And so certainly we can then test this framework with a very simple system set, right? And that's, again, things that we've done and measured vapor pressures of individual compounds, and say, well, do they behave according to this equation? Does this equation apply to the systems that we observe here? So we can then do very simple experiments, almost a physical chemistry experiment, to sort of try to evaluate this approach. Is it applicable to organic aerosols? Then you could apply it here to the more complicated system where you can't do the sort of first principles calculation because you don't know the parameters that you need to run in the model. Right? So we do that as well. I mean, I could have showed a bunch of those sort of detailed results. This is sort of a high-level sort of seminar. We do the chemistry experiments. I showed just the sort of aging experiments, but we've gone and systematically looked at the effective chemical structure on secondary organic aerosol yields and actually measuring individual chemicals in the smog chamber, looking at the product distributions, looking at the phase partitioning of those things, systematically going through them and trying to understand what the effect of structure, if you add a branch to it, if it's cyclic, if it's PAH or something like that, going and doing those experiments to test the ideas that we're applying in the complicated systems on these simple systems where we actually can measure what's going on. And so what I'd say is we're not taking a statistical approach to it. What we're doing is we have this conceptual model and we can go in and demonstrate that it's consistent with the complex data, but then we can go test it more rigorously with simple experiments. The problem with the simple experiments is they've been the basis for developing the chemical transport models, and what went into those experiments was this idea that these are the four compounds that matter. So if we accurately measure the yields for these 4 aromatic compounds, the models are going to predict what's in the atmosphere. And so what we did is say, well, it doesn't seem like they're predicting what's in the atmosphere. We demonstrated the same thing that's going on in the chamber, and then we could say, well, what else could be explaining it, right? And so you can think about a number of different hypotheses, and certainly our hypothesis is that these low volatility organic vapors, tied up with that is that the yields increase as the volatility decreases, as the stuff gets closer. Conceptually, this makes sense. We've done systematic experiments with homologous series of N-alkanes to evaluate this and calculate what the yields are for these homologous series. So there's a lot of work, both fundamental work that's gone into this, as well as the more applied stuff. And I'd be happy to share papers with you if you're interested in those details. So, and certainly I could have picked, another strategy is I could have picked one very detailed set of experiments and explained, that particular experiment and how we're, attacking one angle of the problem. And that would have been a different sort of talk, and I certainly could have given that sort of talk. To sort of demonstrate the kind of rigor of the approach that we take, as opposed to sort of the big picture conceptual thing that's going on.
Other questions?
Well, I think thank you for the nice presentation. I think this is very comprehensive and impressive work. Actually, in some of our previous field studies, some of the results have corroborated with some of your findings in the laboratory.
Yeah.
So it's a very nice study. So my question may be, most of the studies that in your previous work has been done in a chamber experiment, in a controlled laboratory conditions. But the real world atmosphere is pretty complicated. And in Los Angeles, actually, we have this fortunate a meteorology condition, which people even call it like a gigantic laboratory in Los Angeles. It has very unique trajectory every year. So what might be your take if you want to do field measurements to support your findings in the laboratories?
Well, I think, so last year, right, the CalNext study went on, which was this big, tens of millions of dollars study by DOE and NOAA, and we were involved in this study where we were looking at air quality in the Los Angeles area. And I had a small part, I wasn't a major player in this study. And essentially that study was designed, you could think about designing it as sort of this Lagrangian sort of experiment to try to understand what the evolution is as the pollutants get transferred across the air basin. And so that'd be one way that you could try to evaluate the model. And then in the end, you're evaluating it when you do these comparisons with the chemical transport model, because there's a lot of phenomena that are going on. So those sorts of experiments are one way. And in Europe, we've been designing large experiments to do this sort of thing. I don't know if Leah Hildebrandt, when she was here, if she talked about her Crete data. So that was one site of a series of 12 sites that we had set up across Europe to look at basically the transformation of the aerosol as it was affected across Europe. So that's another way, again, to sort of address this, so we can observe this in the laboratory. We have a conceptual model of what's going on, and then we can evaluate it. But your point of the atmosphere being really complicated and missing things that are going on here, I mean, that's a worry that I have, right? And I think it's definitely a concern, because certainly before we had this conceptual model that I showed before, which is there are a few VOC precursors and the POA is non-volatile, and we said, okay, well, these are some things that aren't accounted for in that model, and they really change the predictions of what's going on and bring things into better agreement. But oligomerization, I mean, there's lots of other sort of processes that are going on in the atmosphere which may also be relevant here that we may be missing. And so our experiments still have this same problem that, they're in a chamber. We've tried to get closer to the atmosphere, but a smog chamber is not the atmosphere, and it's not as complex. And so that's something that we need to worry about. And so, I don't think this is the whole story. I think this is part of the story, and that essentially some of this sort of big picture chemistry and physics that we've talked about here are things that we need to account for in the models, but it's not everything.
So, any more questions? Any last questions? Yeah.
Dr. Robinson, I'm curious how you would take the future work done in this field and link it to public policy or especially public health.
How we would go that direction?
Yeah.
Yeah. So, I mean, what we're doing right now is trying to improve this process, how it's represented in chemical transport models. So we're doing that by going in and measuring emissions data for a bunch of different sort of sources. You look at the inventories, and these are the sources that we think are important. Let's go get some emissions data for the sources. Let's think about how that changes. So we're working on that. We're working on better representing the chemistry in the models, and this is where the surrogate experiments are coming on. So we're not just semi-empirically fitting the data. Can we take more of a surrogate approach to sort of representing? So we're doing those sorts of things right now, and then doing field work to try to evaluate the model. And that by itself is a very large activity. But certainly from a health perspective, so if we look at what the Loveless Institute is doing or something like that, right, where they've got a diesel engine, they got a bunch of rats, and they're exposing it to relatively low dilution diesel exhaust, and then they're using that toxicity, using a bunch of toxicity measurements and saying, where they're comparing a bunch of different sources, right? Because what EPA wants to know is which source is causing the health effects, so we can reduce emissions for those health effects. And so the question there, in my mind, with this is if there are all these transformations that are going on in the atmosphere, what is this simple experiment that is being done at Loveless, that you're just looking at the fresh diesel particles, is that telling you, what's really going on in the atmosphere? And so we've certainly been talking a lot about, trying to investigate, essentially, and there's been some work that's looked at, the toxicity of transformed diesel exhaust, and there's certainly, by some measures, it's more toxic, but I think that's something that needs to be done a lot more as well. And so again, EPA has this source to effect paradigm, which makes a lot of sense from a regulatory perspective, but we've got to make sure that we're not misattributing what the effects are, because we have this too simple conceptual model of what the is exposed. So thinking about experiments where we actually look at these sorts of transformations, and I know at Harvard they're doing this. There's the Teresa project at Harvard, where they've got one of these chemical reactors, and people are starting to do this. And certainly we're interested in doing it, and we don't have the right collaborators right now, at least in Pittsburgh. We're also pretty busy doing some of this other stuff as well. Does that give you a sense of the direction that you want to try to head? Anything else?
Well, let's thank Dr. Robinson for a real tour de force in this review of this really important aspect of atmospheric chemistry. Thank you.